In 1975, after 3 long years of excavating, hauling, placing, and compacting soil across the Teton River, Teton Dam topped out at 305 feet or 93 meters high. Built by the Bureau of Reclamation, the dam was the flagship component of the Teton Basin Project of southeastern Idaho, meant to provide flood control, power generation, recreation, and irrigation water supply for farmland in the Snake River Valley. Not everyone was enthusiastic about the dam. The benefits were significant, but many felt that they didn't make up for the environmental impacts, let alone the $100 million price tag. Like most major water projects, it was controversial from the start, but politicians and dam advocates eventually won out. The lawsuits were resolved, and the earthen dam reached its final height at the end of 1975. Other parts of the project were still under construction even as the dam wrapped up. In particular, the contractor was behind on a tunnel through the left abutment of the dam called the River Outlet Works. This structure was needed to make controlled releases downstream. By the time the dam itself was done, the smaller auxiliary outlet tunnel on the opposite side was the only way to release water. Even so, the Bureau was eager to put the dam in service. Waiting for completion of the River Outlet Works would mean losing out on a whole year of valuable spring runoff that could be put to use, irrigating fields, floating boats, supporting fish, and generating electricity, so the Bureau decided to start filling the reservoir anyway. The first filling of any reservoir is a risky process. No matter how much you plan a dam, you never know how it's going to respond to the immense pressure of actual water. Like many projects of its kind, Teton's designers required that the initial fill be moderated, only allowing the reservoir to come up by a maximum of 1 foot or 30 centimeters per day. As it filled, engineers and technicians performed daily inspections and monitored the water levels in nearby wells. The goal was a measured process, loading the structure slowly so they could catch any problems and respond, even lowering the reservoir back down if anything seemed off. Early in 1976, though, after a particularly snowy winter, it became clear that the spring melt was going to send a lot of water their way. Without the River Outlet Works, the dam's ability to release water was limited. The auxiliary outlet tunnel just couldn't handle the flow they needed. That meant the reservoir would have to fill faster than the foot-per-day limit. So they relaxed the limit. The dam seemed to be holding fine anyway, and there really wasn't another choice. As the summer got closer, the reservoir was nearly full, just a few feet shy of the spillway. On June 3rd, engineers were doing their daily routines when they noticed water springing from the right abutment. The leaks were pretty far from the dam. It's not completely out of the ordinary for little seeps to form in the vicinity as local groundwater levels respond to a new reservoir. 2 days later, though, on the early morning of June 5th, there were more leaks, and this time they were on the dam itself. Engineers quickly knew something was seriously wrong. The water coming through the west side of the dam was first noticed around 7 a.m. By 10 a.m., the project's construction engineer was peering into a tunnel carved through the embankment that was tall enough to stand in and extended into the dam as far as he could see. I'm Grady, and this is Practical Engineering. Teton was a zoned embankment dam, meaning it was made of different kinds of compacted earth, each serving a different function. That soil came from borrow areas near the site of the project to minimize the cost of hauling it. Roughly 10 million cubic yards, or 7.5 million cubic meters of material were excavated from the abutment areas and even from the bottom of the river, hauled to the site and placed in thin layers, then compacted into place. In the center of the embankment was Zone 1, built from wind-deposited silt, known as less, that covered the upland areas at the top of the canyon around the dam. This zone of fine particles was the core of the dam, meant to provide the watertight barrier to prevent leakage. But even if the dam itself was watertight, there was another engineering challenge. Below all the less in the upland areas, the geology in southeastern Idaho gets a lot more complicated thanks to an eruption of the Yellowstone supervolcano about 2 million years ago. When a massive volcano erupts, it doesn't always flow like liquid basalt. Instead of oozing, it explodes into a gigantic cloud of hot, searing, pulverized rock that's somewhat misleadingly called volcanic ash. If that ash is hot enough when it lands, the weight of the layers above it squeezes the particles together into solid rock called welded tuff. But as that material cools, it also shrinks and cracks. Hot gases create voids. Soil and rocks picked up by the ash cloud create porous rubble zones. And seismic activity over millions of years breaks everything even further, leaving joints and fissures. As a result of all those geologic processes, Teton's foundation was essentially Swiss cheese. The Bureau of Reclamation carried out some early tests to try and seal up the porous rock with grout. Just a few holes to see how well it would work. They estimated it would take about 260,000 cubic feet of grout injected in the holes to seal them up. It ended up taking more than double that. Some of the holes simply didn't stop taking grout no matter how much they put in. The next year, they drilled holes to check if the grout worked out. The core samples they recovered were just as broken, fractured, and porous as before the pilot program. It just wasn't going to work out, so the Bureau came up with a new plan: core trenches. If they couldn't seal up the worst top layer of foundation rock, they would just take the material out and replace it with something more watertight. So the designers of Teton incorporated key trenches below the dam intended to cut off the flow of water underneath through the foundation. The trench was wider in the valley but narrower up the abutments to help the dam lock in to the steep canyon walls. At the bottom of the trench, the Bureau went ahead with the grout curtain idea but slightly modified from the pilot program. This time they drilled 3 rows of holes. The outer rows were grouted first to create an initial seal. Then grout was injected into the center row with the goal of completely filling the space without losing all the material upstream and downstream. Despite what they learned in the pilot program, the project required significantly more material than expected, ultimately injecting roughly 600,000 cubic feet or 17,000 cubic meters of grout into the dam's foundation. Once that was finished, crews backfilled the core trench along the bottom of the dam with the Zone 1 silt to create a watertight barrier. On the surface, it seems like a reasonable course of action. You have seemingly watertight materials from deep in the foundation all the way to the top of the dam, first with the grout, then the core trench, and finally the embankment on top. But some of the decisions made in that trench would prove fatal. We'll never know the exact single cause of failure since a lot of the evidence was washed away, but 2 teams of engineers investigated the wreckage, one from the Bureau of Reclamation and an independent panel. Both reached basically the same conclusion: the dam's design was doomed to fail all along. As the reservoir filled up, it reached the upper layers of rock that were the most fractured and started flowing into it. With no real barriers, the flow could move freely all the way to that silty core trench, and somehow it could also get past it. It could have been that the water flowed through windows in the imperfect grout curtain underneath. It could have traveled along an area that wasn't well compacted during construction. Or the reservoir water pressure could have resulted in a phenomenon known as hydraulic fracturing, the same process used in oil and gas production that you probably know as fracking. If water pressure exceeds the forces holding earthen material together, namely the weight of the soil above, it can force open cracks, creating pathways for seepage. It's possible all 3 contributed to the flow getting past the dam. All we know is that it found a path, and once it got past, it could flow freely in the cracks of the foundation downstream. At 7 a.m. on June 3, 1976, 2 days before that collapse, the seepage was spotted on the right abutment. At that time, there was no way to know what path that water was taking. It was running clear, meaning it wasn't carrying away soil yet, but it was a hint of what the water was doing inside that fractured rock. That Zone 1 material was well compacted, but all it took was a small area of loose soil to break free. The issue is that even when well compacted, it's not that hard for material to break away. Silt is a highly erodible material. Large particles like gravel and coarse sand mechanically lock together, plus they're heavy, making it harder to pluck them free. Microscopic clay particles often stick together through intermolecular forces, but right in between you have silt and fine sand. Too small to mechanically lock together, too large for intermolecular forces to dominate, and very lightweight. The less soil from the plains along the river was practically the worst choice of material you could make for the core of an embankment dam. Paradoxically, that erodibility was made worse by the silt's strength. You'd think that a strong material would be a good thing in a dam, but in this case, you'd be wrong. Where other materials would naturally slump into voids as soon as they formed, healing itself, the silt was strong enough to maintain vertical walls and a roof. As it eroded away, it formed a tunnel, a process known as piping. Those pipes just created more space for water to flow and erode more of the dam away from the inside. Another contributing factor was the narrow width and steep sides of the key trench. The soil distributed downward forces laterally into the rocky walls of the trench, kind of like an arch bridge converts loads into horizontal thrusts at the abutments. Had the full weight of the soil propagated straight down, it would have likely collapsed any tunnels forming through the core, but the arching action allowed them to stay open and grow. Downstream, the rock was loose and the fractures and voids were large enough to carry soil particles away. There was a free exit for the dam's internals. While Zone 2 of the embankment was intended to be a filter that would keep any erosion from carrying soil away, the actual seepage simply passed underneath it like it wasn't even there. By the morning of June 5th, a channel had been hollowed out under the dam. Staff saw water exiting at the toe, and it was quickly getting worse. At 10:30 a.m., a muddy geyser erupted from the face of the dam. Operators sent bulldozers to try and fill the hole, but the machines were swallowed by the eroding embankment, and the operators had to be rescued with ropes. Only 30 minutes later, a sinkhole opened up on the upstream face below the reservoir, giving the water a more direct path through the dam. Multiple witnesses saw a terrifying whirlpool form. The reservoir was draining like a bathtub directly through the center of the dam. More dozers tried in vain to push material on the upstream side to close the hole, but it was too late. The erosion worsened, allowing more flow, causing even more erosion in a runaway feedback loop until finally the embankment gave way at about noon, only 5 hours after the leaks were first noticed. A wall of water thundered through the hole in the embankment. The breach wave moved quickly downstream in the Teton River, widening out once it left the canyon. The closest town in its path, Wilford, was basically wiped from the map, with nearly all the homes there swept away. Further downstream, Sugar City and Rexburg were similarly decimated, with the vast majority of the buildings rendered a complete loss. Then the smaller farming communities of Hibbard and Salem were inundated, homes and livelihoods washed away. The breach killed thousands of livestock, destroyed railroads, bridges, and farmland, and left thousands without a home. Ultimately, 11 people lost their lives. Had the failure happened at night when no one was watching the dam, it could have been hundreds or even thousands more. Investigations concluded that this was not a freak accident. The challenges of erodible soil and fractured geology were well known long before the 1970s. The Bureau simply didn't spend enough money to address them. In the end, it was a simple case of frugality over safety. As one investigation said, defensive measures such as rock surface sealing and adequate filters were well within the state-of-the-art at the time Teton Dam was designed and should have been used. But even though it wasn't a novel failure mode, the impact Teton had on the engineering community was enormous. To see a brand new structure, built by one of the most technically competent agencies in the US, fail in such dramatic fashion was catalyzing in many ways. The federal government responded by standardizing dam safety guidelines across all federal agencies involved in dam construction, rules that are still in place today. The event also spurred research into filter and drainage design for dams, along with better understanding of the mechanisms of hydraulic fracturing. Finally, it showed engineers everywhere what was possible when geotechnical issues aren't taken seriously enough. The very first dam I worked on in my career was very much Teton-esque. It was designed by another firm, but during construction they realized that the foundation was much worse than expected. There were pores, fractures, and even caves below the dam. They had to shut down the job and re-engineer it entirely. Our solution was a deep cutoff wall. It basically involved running an enormous vertical chainsaw along the length of the dam, then filling the trench with a watertight mix of rock cuttings, cement, and bentonite clay. I vividly remember working through the complexities and challenges of dealing with that foundation material. It's really easy to understand these failure modes in hindsight, but when you're working on a real project, it's hard to visualize how soil, rock, and pressure will actually behave underground. Things get pretty abstract and you can lose sight of the stakes. It's hard to explain what it meant to have that example of Teton at the top of mind for everyone on the design team. For all the computer models, testing data, and equations, we also had a real-life example of what could happen if we got it wrong. It was grounding in a way that textbooks and Excel spreadsheets are not. And I like to think that's how we honor the victims of engineering disasters, to share the stories and keep the lessons from being forgotten, to make sure it doesn't happen again. The story of Teton Dam is in many ways a story about geology. I think it's kind of human to just think the ground is the ground. It does the same job no matter where you are. The truth is that geology affects us in all kinds of interesting and weird ways. My fellow creator, Joe Scott, recently released a documentary where he visited the oldest and the newest places on Earth. It's this fascinating exploration of geology, how it affects us, and the wild shift in perspective you need to really wrap your head around the whole topic. The documentary is less a story about the rocks and more about how they help us reframe our understanding of the Earth. I love it, and I'd love for you to check it out on Nebula. If you haven't heard, Nebula is a streaming service built by and for independent content creators, including a lot of my favorites. The goal is to elevate the experience of online video, reducing the barriers between you and us. There are no ads, just a curated collection of the most thoughtful videos on the internet. And most importantly, Nebula's working hard on original, higher budget projects that you can't find anywhere else, amplifying the creative power of some of your favorite hosts. Joe Scott's new documentary is just one example. Jason from Not Just Bikes has a cool series, Day Pass, about experiencing as much of a city as possible in a day on public transit. Sam from Wendover Productions has a bunch of interesting and wacky projects, including jet lag. It's really cool to see what some of my colleagues and friends can accomplish with the support of Nebula, especially because this is not a high-price subscription. In fact, if you type in go.nebula.tv/practical engineering or click the link in the description below, right now you can get a full 50% off the normal price. That's $30 for an entire year's access, or just $250 a month. And if you really don't like recurring subscriptions, a lifetime membership is $200 off. Pay $300 for lifetime access for everything Nebula has to offer. That's go.nebula.tv/practical engineering, or just click the link. Thank you for watching, and let me know what you think.